Okay, this is 2.6 for Pre-Calc Part 1. Today we're just going to talk about identifying horizontal and vertical asymptotes. We are going to talk about end behavior of rational functions, and that involves limits and then the graphs of the rational functions. We'll get a little bit into that. A rational function, basically, guys, is when you take a polynomial and divide by another polynomial. Okay, we just have to make sure that the q of x down here doesn't equal 0, because obviously you can't have a 0 in the denominator. So it says to find the domain of f and use limits to describe its end behavior at values of x not in the domain. Okay, so the first thing we'd want to do when we find domain is we want to set the denominator equal to 0. So x equals 2, which means really x can't be 2. That's the only number that we cannot use in this problem. So our domain would be all reals except 2. Okay, we've done that a million times. Now it says describe its behavior at values of x not in the domain. Well, the only x that's not in the domain is 2. So what we're going to do is we are going to do the limit of f of x as x approaches 2. Now, here's the issue. When we graph this, okay, here's our vertical asymptote, okay, all right. Here's our graph, all right. What we want to do is when we approach a specific number, okay, and really what the limits we've done so far have been to infinity or negative infinity. Well, now we're doing a limit as x approaches a number. Well, when we do that, what we want to do is we want to approach the number from each side. Okay? So this 2 to the minus, it looks like a minus sign's in the exponent. That 2 minus means we're going to approach from the left side. So as I approach the left side, as x is getting closer to 2, my graph is going down infinitely. Now, the 2 plus means we're approaching from the right. Okay, so as I look at my graph, as x gets closer to 2 from the right-hand side, I see that my graph gets infinitely big. Okay, so when we're taking a limit and we're approaching a specific number, we want to approach it from the left and the right. Okay, next. One of the simplest rational functions is the reciprocal function. So we've done a bunch of stuff with that before. This function can be used to generate other rational functions. Sketch the graph below. Well, we already know what this looks like. Okay, that's 1 over x. Okay, we already know what that looks like. That should not be a big issue. All right, so it says describe how the graph of the given function can be obtained by transforming the graph of the reciprocal function f of x equals 1 over x. Identify the horizontal and vertical asymptotes and use limits to describe the corresponding behavior. Sketch the graph of the function. Okay, lots of stuff to do here. First things first. Okay, if you have something like x plus 3 in the bottom, okay, that's going to be a horizontal shift. Okay, so we're going to shift to the right 3. Actually, not to the right. We're going to go to the left 3. Excuse me. Because it's x plus 3. Okay? So we're going to go, left 3. Now, when there's a number on top, if it's just a number, that's going to be the stretch. So we're going to stretch 2. All right? Vertical asymptote. Okay, vertical asymptote is x equals negative 3 because, again, we want to set the denominator equal to 0. So negative 3 plus 3 is 0. Horizontal asymptote, y equals 0. Okay, now remember your rules for horizontal asymptote. Okay, if the degree on top is smaller than the degree on the bottom, then the horizontal asymptote is 0. The degree of the top is actually 0 in this case because there's a constant term there. Okay, now when we draw this, okay, here's our vertical asymptote, and then our horizontal asymptote is here. Okay, here's what our graph looks like. All right. Again, it's a variation of 1 over x, guys. So all we're doing is we're just shifting the branches around. So now, this time, I'm actually going to do 4 limits. And you're saying to yourself, how in the hell are you going to do 4 limits? Well, here's what's going to happen. Okay, we're going to take the limit of g of x as x approaches infinity and negative infinity, like we normally do. Okay? So we're doing end behavior. But see, here's the problem. There are really 4 ends to this problem. There's an end here, there's an end here, there's an end here, and there's an end here. So really we have to find 4 limits, okay? So the first thing we're going to do is we're going to find the limits involving the infinities, okay? So the limit as x approaches infinity, not affinity, is 0, and negative infinity is 0, because again, the graphs are approaching the x-axis. Now, we have a vertical asymptote, which means that we are going to approach negative 3 as x approaches negative 3 from the left. So as x approaches negative 3 from the left, it's going towards negative infinity. And then the limit as x approaches negative 3 from the right, so here we're coming in from the right, here's our graph, it's getting infinitely bigger. Okay? So when you have a vertical and a horizontal asymptote, and they ask you to talk about the behavior, okay, you want to approach, okay, you want to do the infinities, and you want to do the number of the vertical asymptote. Okay? All right, as far as part B is concerned, all right, so let's talk about what we're going to do here, because this really kind of throws a wrench into things, okay? You're dividing by x minus 2, but it's not just a constant on top, it's a 3x minus 7, which really makes a big difference. So what we're going to do, let me erase some of this. What we're going to do is we're actually going to do synthetic division on this to find out what the top divided by the bottom actually is. Over here, we didn't have to do that. You had a constant on top, you had an x plus 3 on the bottom. It was pretty easy to manage. Here, it's different because of the expression on top. So what we're going to do is this. X minus 2, okay, is the denominator, which means that we put 2 in the box. Now, coefficients are easy, 3 and negative 7. So I do synthetic division. It helps if I drop the correct number. That always helps. 3. 2 times 3 is 6, minus 1. So what does that mean? Well, remember, when you divide, you do a degree less. Well, the degree of the top is 1, x to the first. Okay? Well, that means I have a constant, 3. And then I'm going to write the remainder as a fraction. And to do that, I just do the remainder, which is negative 1, so minus 1, divided by what I divided by, x minus 2. Now, if I switch those, if I just reversed these terms, okay, I would get negative 1 over x minus 2 plus 3. Now, here's what happens. I want you to take a look at something. There are 3 things that are happening. First, the negative sign, we are reflecting over the x-axis. Okay? That takes care of the negative. 2, we shift 2 to the right. And then finally, the plus 3 after means we shift up 3. Okay? Now, with these 2 shifts, when you shift the graph up or down or left and right, that also is affecting the asymptotes as well. Your asymptotes are shifting. Now think about this for a second. So if y equaled 1 over x, horizontal asymptote, y equals 0, vertical asymptote, x equals 0. Well, look what happens here. The vertical asymptote is x equals 2 because we shifted 2 to the right. So that means the vertical asymptote went from x equals 0, 2 to the right, which gives you x equals 2. The horizontal asymptote was y equals 0, okay? But this number out here tells us that that horizontal asymptote shifted up 3. So there's my horizontal asymptote, okay? So when I graph this, okay, here's my vertical asymptote, here's my horizontal asymptote. Now, remember, whoops, that was terrible, sorry. You guys know what the graph looks like for 1 over x. Well, it's flipped upside down because of that negative right there. So when I do my limits, so the limit of f of x as x approaches infinity, limit f of x as x approaches negative infinity. So those first. So as x approaches infinity, what's my graph approaching? 3. What's the limit as x approaches negative infinity? My graph is getting towards 3. Now my limit of f of x as x approaches 2 from the left. 2 is our vertical asymptote, so now we're approaching from the left. My graph is approaching infinity. My limit as x approaches 2 from the right of f of x. Okay, so now we're coming in this way. Here's my graph, and it's going down forever and ever and ever to negative infinity. Okay? You can kind of see what's happening here, I hope. Notice that when we approach the asymptote, the vertical asymptote, when x approaches the asymptote vertically, we get infinity and negative infinity. When we approach infinity or negative infinity, we wind up getting the horizontal asymptote. That actually happens on purpose. Okay? So this one's a little bit more involved. You're going to practice this a lot more, and we can go over it a little bit more when you want to. All right, last one. Find the horizontal and vertical asymptotes of x squared plus 2 over x squared plus 1. Use limits to describe the corresponding behavior of f. Now, a couple things. One, let us find the vertical asymptote. So to do that, we set the denominator equal to 0. Well, unfortunately, there is no real number solution to that equation. So there is none. Horizontal asymptote. Degree on top is the same as the degree on the bottom, 2 and 2. So that means you take the coefficients in front and divide them. Well, 1 divided by 1 is 1. Okay? So what happens here is that we have horizontal asymptote at y equals 1. Okay? Now, remember back here, we did the limit as x approached infinity and negative infinity. So right here. And what happened? The limits were the number of the horizontal asymptote. Well, that happens here. So the limit as x approaches infinity of f of x equals, well, what's the horizontal asymptote? 1. The limit of f of x as x approaches negative infinity, 1. Now, unrelated, this is what that graph looks like, okay? There's no vertical asymptote, so these are the only two limits you're going to find. You're not going to have a limit approaching a number from the left and the right because there is no vertical asymptote to approach. So in this case, you only do the infinities. All right, this is the last one. Excuse me, I'm sorry. It says find the asymptotes and intercepts of the function x to the third divided by x squared minus 9 and graph the function. Now, this one's different, okay? Vertical asymptote, okay? Set x squared minus 9 equal to 0, add 9, take the square root. So that is your vertical asymptotes. Actually, you have 2, plus or minus 3. There is no horizontal asymptote, and the reason why is the degree on top is bigger than the degree on the bottom. Now, when that happens, okay, there is the possibility of something called a slant asymptote. Now, that means exactly what it says. It's an asymptote, it's a slanted line. Now, how do you figure out what that is? Well, what you have to do, and we did not talk about this earlier in the chapter because I didn't think we needed to use it, but in this case we do. If we can figure out an easier way to do this, I'm all ears. We have to do long division, okay? Long division with the polynomials. So what goes on the bottom goes outside, what goes on top goes inside. How many times does x squared go into x to the third? X times. X times x squared minus 9 is x to the third minus 9x. Now I subtract that whole thing. X to the third minus x to the third is 0. Now there's a 0 here, so minus negative 9x is positive 9x. Now we can't do any more with that. There are no terms to bring down, nothing. Besides that, 9x doesn't go into x squared. So here's what we have. We have x plus, this is the remainder, 9x over what we divided by. Okay? Now, if I switch that around, that's 9x over x squared minus 9 plus x. Now, if you notice, that looks a lot like this right here with the plus 3 after the fraction. Okay? But this time there's a plus x. When that happens, that means you have a slant asymptote, y equals x. It's whatever this is. Okay? So it's a slanted asymptote. So, if we go to graph this, okay, so I've got my vertical asymptotes at 3 and negative 3. Now, when I do my slant, whoops, did it also, oh, one more thing I have to do. Find the intercepts. Whoops. Okay, so when I find the intercepts, okay, so the y-intercept, let x be 0. So you put 0 in for x, put 0 in for x. You get 0 divided by negative 9, which is 0. The x-intercept, you let y equal 0. Okay, so now, let me erase this. So now, I'm going to let 0 equal x squared over, x to the third over x squared minus 9. Well, if I multiply both sides by the denominator, those go away. Well, 0 times this is 0 equals x to the third. Well, that just means x equals 0. So in this situation, the y-intercept and x-intercept are the same. They're both at the origin. So that's that point right there. Now, your slant asymptote is the y equals x. So you draw a dotted line right here. Okay, that's the slant asymptote. Now, it would be my suggestion at this point that you just graph it on your calculator, and you will see that that's the middle, and then these are the branches at the end. Okay, so I would definitely use my calculator to do that. All right, so we're going to work on this in class. If you guys have any questions, you are more than welcome to ask. You're going to be working in pairs. You'll find out about what's going to happen with that on Thursday. Okay, see ya.